Hi everyone, my name is Dina Katabi. I am the Thuan and Nicole Pham professor at MIT. And I'm very happy to be here talking to you today. So today I'm going to talk to you about new technologies that use AI and radio signals to monitor sleep, activities, vital signs, and many interesting information about users without any body contact. So let me tell you what I mean by this. I'm sure all of you guys have a Wi-Fi box at home. Now imagine if that Wi-Fi box was smarter, was able just to analyze your sleep, your gait, your breathing, your heartbeats, activities, all of that stuff without touching your body, just by analyzing the radiomagnetic signal in the environment. This is exactly what we did in my research group at MIT. We invited a box that very much looks like your Wi-Fi box at home. We call it the Emerald box. And it sits in the background of the home, and it analyzes the radio signals using machine learning algorithm. And it uses a radio signal that bounces off our human bodies. And by analyzing them with AI, it can get your sleep, your gait, your mobility, breathing, heartbeats, activities, all of that without having you wearing sensors on your body or asking you to do anything specific, completely passively. So let me show you an illustrative video of this. So here is the home. The radio signal spreads inside the home. It reflects off the human body because our bodies are full of water. And some of these signals will come back to our device that you see here. And here it can detect, for example, a fall, inform the caregiver via text, email, or phone call. I want to show you some of the experiments from my lab. So this is my student, and you see this is one of our offices at MIT. Now, our wireless device is not even in the same office. We're going to monitor this person using our wireless device from the adjacent office. So here you see this big arrow, and our device is in the adjacent office behind this wall. So I'm going to play this video, but I want you first to look at this red dot here. And as he moves, you can see that the red dot is moving with him. So basically, our device is getting his exact location and is showing it as this red dot on the floor map. And remember, we are able to track his motion accurately without any sensors or wearables. Okay, so of course, everything that we do, we compare to the gold standard. So in this case, we can track this location accurately, and we compare to something called the Viking motion capture room, and it can localize a person very accurately, and our accuracy in comparison to that gold standard is 98% in identifying the exact location of the person. Now, once you start having the ability to track people and how they are moving inside the home, now you start getting much information about activities and environments. So now you can detect, for example, how often the person enters the kitchen to get, and how often he goes to the fridge, for example, so that you can start getting information about their eating behavior. You can also check when the person sits on the TV couch, and you can use that information, for example, to tune the TV to their favorite channel. You can also start asking questions about mental health and depression. For example, if you see the person is staying in their bedroom, they are not talking to anyone, they are not interacting with anyone, hardly they leave the home, this is a sign of withdrawal. So basically, by being able to analyze how people move in the environment, not only you get health information, but also you can get information about user activities that you can use to create smart environments, smart homes, smart offices, etc. But we can monitor more than just location of people and movements. In fact, we can monitor sleep. So when you go to sleep, your brain waves change and you enter different sleep stages. These are called awake, light sleep, deep sleep, and rapid eye movements, or REM. Now, these sleep stages, of course, are very much related to sleep disorders. And in the US in particular, for example, 1 in every 3 Americans has a sleep problem. And sleep problems are quite common. And of course, by being able to analyze sleep and analyze sleep, not just to discover whether somebody is awake versus asleep, but to understand their sleep stages, now we can help the doctors and help the user himself understand his sleep and try to improve it. But this is not the only thing. In fact, sleep also is related to a variety of diseases. So particularly, for example, REM, this stage here, rapid eye movements or REM, this stage actually is very much associated with mood disorders. Like in depression, for example, people tend to have REM early on in sleep, too early. And Alzheimer, for example, and cognition problem typically are associated with disruption in the slow wave that we see in deep sleep. So imagine if we can get this detailed information about people's sleep and we can get it easily at home. Not only we can help them improve their sleep, but also we can inform them about discover whether somebody, for example, is slowly relapsing into depression, or some people, they have disturbances that could be correlated with a sign of Alzheimer potentially, and ask them to go and check with the doctors. So today, if you really want to get sleep to this level of detail, you have to send someone to a sleep lab, and they put all of these electrodes on his head and body and ask him to sleep like this. Now, of course, having to sleep with all of these electrodes is very uncomfortable, but also you cannot do this often. I mean, you can just send someone to a sleep lab once every I don't know, once or twice, or maybe every few months, but you can't really have them sleep all the time in a sleep lab or wear all of these sensors on their body. So let me show you how we can measure sleep with our device. Here is our device. It transmits very low power wireless signal, analyzes the reflection from the person and the environment, and using AI algorithm, it can spit out the sleep stages of the person throughout the night. So here what you see on the screen, this graph is something called the hypnogram. So when you go to a sleep lab, they tell you for every 30 seconds, whether you are in awake, whether you are in REM, whether you are in light sleep, and that is called hypnogram. And this is exactly what our algorithm can provide you, but it can do it for every night when you are actually sleeping in your own bed, like the person you see in this video, and without having to wear any sensor on your head and body. And we compare our algorithm with the gold standard, which is like sending a person to a sleep lab, like you have seen in one of my previous slides, and have them putting all of these electrodes on their head and body. And the accuracy of generating this hypnogram and every single sleep stage event is 80%. Now, 80% actually is very high, because it's in fact is comparable to sending someone to a sleep lab. Because when you send someone to a sleep lab, they sleep with all of those like EEG signal and all of those devices on their body. But later someone comes, and these are the sleep technicians, and they look at the EEG signal. And for every 30 seconds, the sleep technician has to say, okay, so the person is in light sleep, in deep sleep, etc. But the one thing that is important to notice is that because this is a human deciding what is the signal is, so if you take 2 sleep technicians and give them the same signal from the same sleep lab on the same night for the same person, actually they have differences between their judgment. On average, their consistency is about 83%. So we are able to generate this automatically in the person's home, and we have an accuracy of 80%, which is pretty close to this 83%. Now, this is a person who is sitting like you or myself here, but what you see on the screen is his inhales, exhales. This is his breathing. And we ask him to hold his breath, and you see the signal stays at a steady level because he exhaled, he did not inhale. And now again, everything that we do, we compare with the gold standard. In this case, we compare with an FDA approved chest belt, which is the typical thing that doctors use, for example, in sleep labs to measure breathing. And the accuracy in tracking that breathing signal is 97%. Now, I want to zoom in on that breathing signal. So what you see here is the same thing that I showed you before. These are the inhales, these are the exhales. And you see small blips on the signal. These are actually his heartbeats. So we are able, the wireless signal is very sensitive. When the wireless signal reflects and bounces off our bodies, it actually gets impacted by the pulsing of our blood. And that even the pulsing of our blood leaves its impact on the wireless signal. And using our algorithm and our models, we can extract that information the same way as we extract also breathing and sleep and the motion that I talked to you about. I want to tell you at a high level how we can generate these devices. Now, of course, I cannot tell you all the details, so I'm going to just talk really very much at a high level. So let's think about it together. So when you have a wireless device, you can transmit a wireless signal. We know that wireless signal traverse walls and obstacles, like you can hear or you can connect to your wireless router, even if you are not even if you are not in the same room. But wireless signal also reflects of the human body, and some of these minute reflections will come back to our device. So we receive them back. And if you think about it, there are multiple ways that we can analyze this signal. One simple equation that we all know is that distance is equal to the reflection times multiplied by the speed of light. So for example, we can track the distance, we can track the location and how this person is moving by measuring the reflection time of the wireless signal and multiplying it by the speed of light. So this is a very simple thing, just like the first level if you want to track people using wireless signals. Now, of course, life is not that simple, and we cannot simply use this equation. In fact, this equation is what is typically used in radar systems, so that this kind of behavior. Unfortunately, we can't just simply use this equation because indoor environment and the health signal that we are seeking are much more complex than that. So specifically, if you try to just simply take these kind of equation and signal processing that is typically used by radar and try to use them in the home to track people, you get something called multipass effect. So the signal not only reflects of the human body, it reflects of all the objects in the environment. In fact, you can get these secondary reflections. So the signal might reflect of the person, and then of the chair, and then of the wall, and you can start seeing all of these fictitious people that as the person moves, all of these side reflections move with him. So instead of getting the this simple equation where the one signal or one reflection comes from one person, you get these like different reflections and a mess of reflections, or what we call multipass in communication. And it's going to be very, very hard to extract the person from this mess. So what my group at MIT has done is to use novel mechanisms to analyze this wireless signal that are based on machine learning. And so what we are going to do is not only we're going to track the human body, but we are also going to use this wireless signal to get health metrics from it. And as I said, we are going to do it by using neural networks to analyze wireless signals. Now, I'm sure all of you have heard a lot about the use of deep learning and neural networks to analyze images or to analyze text or audio signals. But now we want to use these neural networks to analyze radio signals and radio waves. So at a high level, what we are doing, we are taking this wireless signal, we are letting it through a neural network. This is just an abstraction. Our neural network, of course, is much more complex than this. And then you train the neural network with data, and eventually you want the neural network to answer some health questions. For example, is the person asleep or awake? And if they are asleep, are they like in light sleep, deep sleep, REM? So we train that neural network to take wireless signal and answer these questions. Now, of course, when you work with radio signals and you are trying to apply deep learning to radio signals, there are many challenges. But one of the things that I want to touch on in this talk is this idea of generalization. Basically, you want to be able to train your neural network with some subset of people in some homes, but you definitely want to take them to new homes and without training again with the new people. So think about, like, for example, if you have a product or you have a device, you trained that device and you created the model, but then if you sell the product to someone, you don't want to ask them to collect data again and train. You want the product to work out of the box. So this is exactly this problem of generalization that we have. And one of the challenges in generalization is, as I said, you train in one environment. So you train with some user, let's say Alice and Bob, you see here. And now you want to take your device and you want it to work in Chris's home and discover Chris is asleep, for example. These are like Alice and Bob will be the source domain and Chris will be the target domain. Now, the challenge, as I said, is that radio signals depend on the environment because they reflect off everything in the environment, as I showed you earlier. So not only they have information about the sleep of Alice and Bob and the movement of Alice and Bob, they have information about also how the room of Alice looks like, how the room of Bob looks like. So many information that have nothing to do with the task that you want this device to do. So what we want to be able to generalize. So which means that we want to remove all of this extraneous information that can be confusing when you take your device and your neural network to in your home. And we want to leave only the relevant information. So this is a general problem in machine learning, but it becomes even much more challenging when you are talking about radio signals. And solving this problem is really hard, and we have many levels of complexity to solve this problem. Just to give you a hint about like one very basic solution, it's not a perfect solution. We do something that is way more complex than this, but it's just to get you started on thinking about it. One approach to try to address this problem of generalization is what we call adversarial domain adaptation. So specifically, say that you have some signal, radio signal, and you want to encode the signal to some representation, E of X. And then you want to use that encoding to predict some health metric, let's say sleep, for example. Now, what we said is that we want this representation to remove extraneous information and only to leave information related to things that we care about. In our case, let's say sleep. So how do I do this? I can have a third neural network. So here, each one of these boxes is a neural network. So I have now 3 neural networks in my big model. And I can run them and train them together in a particular way. So I want to train them so that eventually this third neural network, which we call the discriminator, so this one I'm going to ask to predict which home the signal comes from. So if this discriminator is predicting the home, it's saying, okay, this signal comes from Alice's home, it comes from Bob's home, it comes from Dina's home. Now, that information is irrelevant. So I'm going to train it to detect the irrelevant information. But I'm going to train it in a particular way so that when I have my cost function, my training function, I'm going to say, okay, eventually as I train more and more and more, my predictor, the neural network that solves the problem that I'm interested in, which is, let's say, to discover the sleep stage, is going to eventually, like, I'm going to decrease this loss. I'm going to make that predictor win. And while the discriminator is a neural network that is interested in this extraneous information, I'm going to put a minus before the discriminator loss, which means that the training is going to make this discriminator over time lose all of the information. So this is one way that we can generalize, remove extraneous information and leave the information of interest. Now, of course, this is just very, very high level. And what we do is much more complex than this. This is just a start to solve the problem, but it doesn't solve the whole problem. And if you are interested, you can read our papers. I just want to tell you more about what we can do with these kind of technologies. So I showed you that we can track people as they move around, but I showed you this video where you can look at this red dot here and you know where this person is. But really just by looking at the red dot, you don't really know whether he's standing or sitting. And when he moves around, you see the red dot sliding, but you don't really know whether he's moving with his right foot versus his left foot. So everything that we are seeing is a red dot that's sliding. We just don't have information about the exact skeleton, exact movement of the legs, none of that. So that was our earlier model. Now I want to show you some of the newer things that we can do that are much more powerful than just a dot on the floor map. So let me move to this more recent technique that we use. And here what you see is, you see these like big frames, the skeletons actually are, the big frame is what our wireless device see and extract and infer. And on the top here, you see the room. And this is just for you so that you can see what is happening in the scene. This is not from the wireless device. This is just information so you know what's going on. So let me play this video for you. And I want you to look now at how these skeletons are moving. Like when he sits on a chair, now the wireless device is giving you a full skeleton that sits with him. When he stands up, it stands up with him. When he moves with his right foot, it's moving with the right foot. When he moves with the left foot, it's moving with the left foot. So now, not only from this wireless signal, we can get a dot on a floor map, but I'm showing you that we can get the full skeleton and start showing the activities of the people. So let me play this video again. And you see again, now we get a skeleton. He sits on the chair. We track him through a wall, remember, without any sensors on his body. So effectively, we are seeing through walls. But not only we can see these skeletons, we can, now that we have these skeletons, we can ask what people are doing, even without seeing them through a wall. So let me show you here. This is, we use the skeleton that we extract to actually inform us about the activity that the person is doing. So here the image at the bottom shows you the ground truth activity, and the skeleton at the top is what we extract from the wireless signal. So let me play this for you. So now he is going to emulate combing his hair, and you see the skeleton looks like he's combing his hair. So he's now moving again. He's going to emulate the drinking water. And you see the skeleton also drinking water. Then he moves. Now he's going to put something in his pocket. You look, skeleton seems to be doing the same activity. He's pointing, skeleton is doing something similar. And again, like he's now looking in his pocket. Again, the skeleton does the same thing. So not only we are start to like get now a skeleton, we also can get activities of what people are doing, and that is very informative because it informs us about like being able to create really these smart environments, smart homes that can understand what people are doing and can track it in the whole view field of the wireless signal. So over the last 3 years, we have been using this technology that we call the Emerald technology to help doctors and patients in a variety of diseases. We have been working with hospitals, we have been working with medical doctors, we have been working with pharmaceutical companies who are interested in running clinical trials. And we worked with patients that have Parkinson's disease, that have Alzheimer's disease. We worked with assisted living community that are interested in like the elderly living and having older people having great life and protecting them. And with people who have immune diseases like Crohn's, with people who have atopic dermatitis, etc. And I want to show you some of the results with actual patients. So everything that I showed you earlier are with students, with healthy individuals. Now let's see also that we can use this technology in diseases to actually get real medical information. So this is our device. This is how it looks. You see here in this red box, this is the device. So as you can see, it's very non-obtrusive. It's really just like you hang it on the floor, on the wall, like a picture frame, and it just disappears into the environment. The person doesn't have to wear sensors, does not have to do anything to be able to monitor them. So let me start with our results in Parkinson's disease. So we worked on, this is part of an NIH center that we work on with some of our medical colleagues. So I'm going to show you first an illustrative example. So here, the emerald box is this green rectangle at the top. And what you see this blue line. So this is a 2 hours trajectory. 2-hour trajectory from the patient. It moves between the bed, the chair here, he enters the bathroom. So this person happens to live in an assisted living community. And here what you see is a floor map of his unit in this assisted living. And we are able to track him just by putting our box in his unit. Now, I want to show you this graph. So this graph is for the same person from the previous slide. Now, every circle here is 1 day in the life of this person. So really what we are interested in looking at is, can we understand his life? Can we just use the device to understand how he spent his time? So we take these trajectories that I showed you on the previous graph, and we generate this graph. Now, every circle, as I said, is 1 day. The innermost circle, this one here, is the first day of the study, and the outermost circle is the last day of the study. So there are here about 2 months of data. Now, the top here where you see 0, this is midnight, and the bottom here is noontime. Now, let's look first at the color blue. So blue refers to the time he is asleep in bed. So you see here the blue at the beginning of the study, like near the inner circles. The blue is very fragmented, which means that his sleep was terrible. While as we progress with the study and get to the outer circles, the blue starts consolidating. So his sleep has improved dramatically. Now, another color here is the green. You see green everywhere. So green refers to the time when he sits on a chair. So actually, if we go back to this slide, you see this chair, and he likes to sit on this chair a lot of times. So he just like wakes up, sits on a chair. So every time he sits on the chair, we capture that and we portray it using the green color here. So you see that this person actually wakes up, sits on a chair. This is mostly what he does with his life. This is a very sedentary life, and this actually is worrisome. Like if you have an older parents or relatives who just like have very sedentary life, that would be something to worry about. So another thing that we see here, a cone of yellow near 8 a.m. in the morning, where I'm moving my cursor here. So you see this cone of yellow around 8 a.m. in the morning. So yellow refers to the time when he enters the bathroom. Now, one of the things that was really surprising to me and my students when we were looking at this data is like, why would someone wake up, like you see the blue ends around 4 a.m. He wakes up at around 4 a.m., sits on a chair between 4 to 8 a.m. and goes to the bathroom at 8 a.m. to do his showering and toileting. Like most of us, we would wake up and just go to the bathroom to do showering and toileting. We don't wake up and sit until exactly a specific hour and then do toileting and showering. So when we talk to the doctor, he was like saying, oh, he understands exactly why this is happening. This is actually because this person cannot do his showering on his own. So what he's doing, he's like waking up, sitting on a chair. Again, remember, he lives in an assisted living community. So he's waiting for the health worker to come and help him taking his bath because he cannot base himself on his own. So this is, of course, very informative. It tells you that this person is really sick to the point that they cannot shower and enter the bathroom on their own. Now, another thing that you see here is a cone of white between 17 and 18. So 17 is 5 p.m. in the afternoon and 18 is 6 p.m. So between 5 and 6 p.m. in the evening, there is dinner in the assisted living community. And this white cone refers to the time he's outside his unit. So he's outside the unit, so he's outside our coverage area of wireless signal. And that's what we portray using white. So what you see is that every day between 5 p.m. and 6 p.m., this person leaves his room and he leaves to have dinner with the rest of the assisted living community. But you see there was a specific day, actually, let me just show you here. So you see this day, on a specific day, he actually came back early. He did not stay to have dinner, and you can see it very clearly here. And this is because he wasn't feeling well, so he came back early. And now, just using this smart Wi-Fi-like box in his unit, we can understand exactly his life, how sedentary he is, how good his sleep, like what are his habits, and even like when he was not feeling well, like detecting events that are different from his rituals. And all of that completely passively without asking him to wear sensors on his body. Now, of course, when you are working with patients and doctors, you want to compare to the gold standard in the assessment of the disease. So if you are assessing somebody who has Parkinson's, the gold standard in assessing the severity of Parkinson is something called the UPDRS. So the UPDRS is a test that has many parts. It takes sometimes more like 3 hours to 4 hours to perform the test. And it is typically performed by a clinician. And what you see here is we plotted on the x-axis the UPDRS part 3, which is the part that refers to motion symptoms, or called the motion score. And the larger the UPDRS, the more severe the Parkinson is. And on the y-axis, we plotted the gait speed that we observe in the home. And every dot here is one patient. And as you can see, basically our gait speed that we measure is highly correlated with UPDRS, and which means that it is highly correlated with the severity of Parkinson's disease. So we are able to measure a metric that is very much related to the severity of the disease. So next, I'm going to talk about monitoring COVID patients. So as part of our work with patients in the Boston area, like when COVID started, multiple of the doctors and like we were working with one of the assisted living community. So they came to us and they wanted to collaborate with us on monitoring their COVID patients. Now, when somebody gets COVID, as you know, they are asked to self-isolate from other people and enter into quarantines. And if you think particularly about patients who are elderly patients who might have cognition problem because they are so old, or patients who just have other comorbidity, it can be dangerous because the patient can, the recovery might not be very smooth and the symptoms may escalate, but the patient might be too sick to realize that their symptoms are getting worse and they need to go to the hospital or contact a clinician. So we started working with COVID patients, and I want to show you some of these results, and these results from patients who live in an assisted living community. So they are older patients. So the first thing I want to show you, of course, is related to respiratory system. So COVID is a disease that affects the respiration of the people and the respiratory system. And here what you see on the slide is the breathing signal of a patient. You see on April 7, where the breathing rate was 23 breaths per minute, and later on April 11, when the breathing rate went down to 18 breaths per minute. So here you see like the breathing rate is 18 breaths per minute, here 23. So as the patient gets better and starts recovering from the disease, we see typically that their breathing rate goes down and approaches their baseline level. And for this patient, it was 18 breaths per minute. Now, another thing, of course, is related to mobility. So we know that COVID affects causes fatigue and affect mobility, and the fatigue just makes people unable to move. As people recover from the disease, we see increase in the agility, as you see here. So here in this video, what you see, the green dot is the patient, and you see two scenarios: the patient moving on April 8th and then later on April 11th after he got better. And in both cases, let me play this, the patient will move from the chair to the bathroom. But you see on April 11th, the patient is much faster and more balanced. Now, of course, sometimes things are not very good. And one of the things that we see happening in some of the COVID patients is very abnormal breathing, like you can see here. So here what you see is the breathing of one of our COVID patients. But instead of these like nice inhales, exhales, you see very irregular breathing pattern. The size of each breath is irregular, and also the duration of the breath. Let me show you more about, like, we discovered that breathing is actually very indicative of recovery. So I want to show you some results from a patient who actually had to be re-hospitalized for COVID. So here what you see, each one of these blue curves is the breathing rate of the individual, and it's a histogram of the breathing rate on a particular day. So you see the first one is on April 8th, here you see it. And each one of these blue curves is a histogram of the breathing rate. Now you see at the beginning, as we progress, from one day to the next, the breathing rate of the patient was getting slower. And you see this green line here, the mode of the breathing rate is moving away from 20 to 15 breaths per minute. So the breathing is getting better and better. However, on April 14th, suddenly the breathing rate jumped up. And as you can see in this graph, and in fact, the patient was feeling really bad and they ended up in the hospital. Now, the patient spent about a week in the hospital, and after they came back, again, you see the breathing rate decreasing, and eventually the patient has recovered. So what we see in the population that we monitored is that there are three types of COVID patients. Some patients are like the one that I just showed you. Their recovery is bad and their breathing rate suddenly jumps, like what you see here. Some other patients are symptomatic, but the breathing rate keeps decreasing as they recover and feel better and better, and eventually they become fine. And the last type of patient are asymptomatic patients, like the one that you see here, where their breathing is fine the whole time, is not changing. They are asymptomatic, they don't have any symptoms. So this gets me to the end of my presentation for you. What I presented to you is new technology that we call the Emerald technology. It's effectively the future that we envision, where we are, instead of just relying on wearables to understand people's behavior and activities and health, we can move to something that we call the invisibles, a technology that would disappear into the environment. It's completely passive, but it can tell about our behavior, about our activities, about our health, and render the environment provide smartness. Like you have smart homes, you have smart environments that will understand people and their behavior and health. I want to end by emphasizing the issue of course, security and privacy. So we designed our technology with, of course, we pay a lot of attention to both privacy and security. So everything that we have is encrypted. Only people who are monitored have access to the data. One other thing that is very important, all of the experiments and the studies that we do are, of course, with informed consent and with the approval of the IRB to ensure that the studies are all ethical. And with this, I will end my presentation and take any questions. Thank you.